Hello Pharma aspirants, welcome to online GDC platform. So, in the series of Pharma Thunderstorm, which is going to helpful in giving you the strong concepts in cracking your competitive exams in your pharmacy field like DI exam, pharmacist exam, AIIMS Pharmacist, as well as other competitive exams like GPAT. Okay, so all these competitive exams you are going to face it. So, these Pharma Thunderstorm series, whichever is going to give you some clear concepts, okay, some of the tricks and mnemonics also we are going to give you, such that you are going to have a clear knowledge on very important topics, right? So, as part of this Pharma Thunderstorm series, today in our pharmaceutical analysis session, we are going to learn about a topic that is absorption bands in UV spectroscopy. Absorption bands in UV spectroscopy. UV spectroscopy, we know that it is an absorption spectroscopy. That means we are going to get different types of the electronic transitions. Okay, so we are giving the energy in the form of light to the molecules. It is a molecular spectroscopy where electronic transitions are going to take place, right? So in those electronic, that's why it is also going to be called as electronic spectroscopy also. And in this electronic transitions, if you are going to find out, there are different types of electronic transitions are possible. Like you have already know about different types of the transitions in the UV spectroscopy. That means sigma electrons, n electrons and pi electrons are also present in the molecules. So the electronic transitions are going to be involving these three types of the electrons. Okay, as per the according to the energy levels, if you are going to see these sigma as well as pi electrons and n electrons we are talking. So from the ground state they are going to be excited to the excited state. Those are called as anti-bonding orbitals. Okay, so homo state to the LUMO state. That means highest occupied molecular orbitals. Whenever energy is going to be given, then the electrons present in the valency electrons, it is going to be there, or otherwise molecular orbitals, it is going to be there. So all those types of the electrons will get the energy and they will excite from the ground state to the excited state. Okay, so those excited states, again you are going to see singlet state, triplet state. So that is based on the spin, electronic spin, it is going to be different. But we know that all the types of the electronic transitions are going to cause the absorption in the UV region. Okay, so we know that UV spectroscopy means generally if you are talking 200 to 400 nanometers, or strictly if you are talking that is 180 to 380 nanometers. This is the exact region that is near UV, we are going to call it as. Okay, so in this near UV, whatever the spectrum we are going to get it, that is due to the sigma electrons, pi electrons, n electrons, electronic transitions are going to take place. So majorly the near UV and far UV, whatever it is there, which is below 200 nanometer, okay, exactly below 180 nanometer it is there. So that is called as vacuum UV region or far UV region, where you are going to see most of the saturated compounds. Okay, that means the electrons which are binding with the sigma bonding. So saturated compounds are going to face the electronic transitions in the far UV region. So most of the unsaturated compounds are going to be getting, that means the electronic transitions. That means whenever we will give the energy in the form of light, that is nothing but called as electromagnetic radiation. Okay, that electromagnetic radiation in the range of UV, whenever we will give as energy to the molecule, then the electrons are going to be excited from the ground state to the excited state. Okay, so most of the transitions, electronic transitions, we know that those are going to be like n to pi star and pi to pi star. Okay, so these two types of the transitions we are going to see in the near UV region, whereas far UV means you are going to see the sigma to pi star, otherwise sigma n to sigma star, like that pi to sigma star you are going to see like that. Okay, but in case of the near UV region, whenever we are going to generally talking about normal UV visible absorption spectrophotometer, if you are going to use for any type of the unsaturated compound, then you are going to see these two types of the transitions. Mostly you are going to observe these two types, okay. And all those transitions are going to cause some spectra, that is called as absorption spectrum, okay. So from that you will come to know the lambda max, right. So where exactly the maximum absorbance it is going to be observed, okay. So all these things are very good. Now in this today's session we are talking about absorption bands. From the electronic transitions, there is a significance of knowing about the lambda max value, right. But from the absorption bands, so these absorption bands will give you which type of the information, what type of the information we will get by this absorption bands. Let us see first what are the different types of the bands normally present in the compounds, okay. That means the unsaturated compounds, are whenever we are giving energy to any molecule, then which type of the absorption bands it is going to give, okay. So if you are seeing the output of any type of the UV spectroscopy, right, we are going to see mostly in the form of a spectra like this, or exactly if you want to know the lambda max, means some compounds you are going to see very good peak shape, you are going to get it, okay. So from this you will come to know this is going to be the lambda max, wavelength versus absorbance we are going to take, okay. So some molecules may have 2 lambda max values also, some molecules will have 3 lambda max values also, based on the type of the solvent we are going to use, and different types of the physicochemical properties are also going to affect. So which lambda max we are going to select for the particular analysis, okay. So that is a different criteria. Now absorption bands, whenever we are going to see any such type of the spectrum in the molecules, by giving the UV energy, you are going to see different types of the absorption bands also, okay. So let us see the types of the absorption bands. Majorly if you see, there are 4 types of the absorption bands occur in the molecules, okay. So alphabetically if you want to remember these absorption bands, means 4 types of the absorption bands, means B bands are going to be the alphabetically if you want to remember, then E bands, then K bands, finally R bands, okay. These are the 4 absorption bands you are going to see in the UV spectroscopy, okay. If you are talking about the intensity wise means these K type of the absorption bands are highly intense bands. Intense bands you are going to see in case of the K absorption bands, okay. So R bands, if you are saying means these are going to be mostly forbidden transitions, these are going to be observed, okay. So in the molecules some of the electronic transitions are forbidden. So in those cases R bands are going to be observed, which are having very less intensity, okay. Whereas among all these 4, K bands are high intense bands, and most of the compounds we are going to observe these K bands as well as E bands. B bands are also going to be there, but a little bit somehow comparatively less than K bands, okay. And in single molecule you may face the presence of K band, E band, B band as well as R band also, but generally these are the forbidden, so you may not observe that. But in a single molecule all types of the absorption bands may occur. Some molecules only 1 or 2 are also going to be occur, okay. So all these are going to be based on the electronic transitions. So let us see which transition is going to cause which type of the absorption band now. First of all, alphabetically if you want to know, that is B band, okay, starts from the B band. So this B band it is going to observed, that means the absorption band which is observed by this B band is due to the pi to pi star transitions, okay. Pi to pi star transitions means pi electrons are going to be involved. That means most of the unsaturated compounds, the electrons where the bonds which are unsaturated, those type of the electrons are going to be involved in giving this B absorption band. Okay, so that's why these B type of the absorption bands are going to be, you are going to see in the aromatic and heteroaromatic compounds. Aromatic means we know benzene containing compounds. Okay, heteroaromatic compounds means we know that is pyrrole, pyridine, like this. Okay, so heteroaromatic compounds, and aromatic means which contain benzene ring. So in such compounds, that means in the ring containing compounds, we are going to see this B bands. So in this B bands means you are going to observe the pi to pi star transitions at the electronic level due to the absorption of the UV light. Okay, and benzene, whatever it is there as an aromatic compound, you know very well that it is an unsaturated compound, aromatic, and it is going to give you the lambda max value at the 255 nanometer. Okay, and the range of this UV lambda max, whenever we are going to see, it is in and around 230 to 270, and the absorption band, it is you are going to observe in this region. Generally peak means a sharp peak we are going to call. Okay, so this is called as peak. So from this you will come to know what is the lambda max, that is normal general criteria. But what is called band? Band means what? You are going to see some of the molecules observe like this. So this total, or otherwise in the negative peaks also you are going to see like this. Okay, so entirely you are unable to exactly take the sharp peaks. Sharp peaks are not going to be observed in such cases. Okay, so like this you are going to see, or otherwise like this, some types of the bands you are going to observe. Okay, so in those cases we are going to see those types of the bands. These are nothing but absorption bands due to the electronic transitions. Okay, and why these absorption bands? Generally we are going to observe transitions. Okay, we know pi to pi star electronic transitions are going to observe. Okay, but why the spectra is like that? Why it is giving sometimes sharp peaks and sometimes a wide band? Why it is going to be like that means, actually there is a reason also for it, because whenever we will give energy to the molecule, okay, so UV light especially it is going to cause the electronic transitions. But as such molecule, if you see, as such molecule, if it is there, it is having naturally vibrational energy as well as rotational energies are also going to be present. Okay, but UV absorption is majorly causing the energy changes in the electronic level, but still there are energy levels related to the vibrational and rotational energies also. Okay, so due to that what happened, you are going to see this bands type absorption bands, we are going to get it. Okay, so only at the electronic level means you are going to get the peaks. Okay, but spectrum how we are going to get it means, that is majorly due to the molar absorptivity value. That means whatever Beers-Lambert's law, in that we know that A equal to epsilon into B into L, right? Epsilon it is called as molar absorptivity, B is the path length, B, L both are same. Okay, so C, it is C actually concentration. So otherwise the path length it is also going to be represented as L also. Okay, but we are talking about molar absorptivity. So the absorbance whatever it is there, it is totally based on the molar absorptivity of the particular molecule. Whatever the energy we are giving, that energy it is going to cause not only electronic transitions, the naturally the molecule itself is having some vibrational as well as rotational energy changes also, but those are not significant with respect to this UV level. Okay, we are only focusing on the electronic transitions in case of the UV visible spectroscopy. Okay, so that's why you are going to observe these types of this absorption bands. And absorption bands, if at all you want to see how these are going to be looking like absorption bands. Okay, so then you need to plot the graph of lambda versus epsilon. So this epsilon you are going to take, the epsilon generally it is going to be highly intense compounds, means you are going to observe 10,000, 13,000 and 20,000 also you are going to see. Okay, so for that purpose the logarithmic value of the epsilon value also you can take it on this y-axis. Okay, so 1, 2, 3, 4, 5 like this the y-axis is going to be there, and you are going to observe the peaks like this. Like this you are going to observe the absorption bands. Okay, so highly intense bands, how these are going to look like, and normally molar absorptivity value which is very less, like how we have seen in the R types of the absorption bands. There are very forbidden transitions you are going to see, and the B bands are also you are going to see the intensity it is going to be comparatively less. Okay, than K bands and E bands. Okay, so because of this you are going to see the absorption bands of the B are going to be observed at the longer wavelengths. Okay, so why this B band absorption it is going to take place means, when chromophores, we know that chromophores are taking the UV energy, so those chromophores are responsible, right? So whenever this chromophore, that means one functional group which is going to acting as a chromophore. So the functional group which is a normal chromophore to any molecule, when it is attached to the benzene ring, when it is attached to any type of the benzene ring, okay, here also or somewhere in and around any type of the, when it is attached to the benzene ring, then you are going to observe the formation of the B bands. Those B bands generally observed at the longer wavelengths. Okay, so that is the information about the B bands, and these are also more, actually sometimes whenever these attached to the benzene molecule at the longer wavelengths you are going to see means more intensity. Okay, that means epsilon value it is also going to be more high intensity in some cases when chromophore is attached to the benzene group directly. In such cases the molar absorptivity value is also going to be very high. Okay, so those bands are called as B absorption bands. So out of this K band, B band and R bands I told you these are the forbidden transitions, and these are also going to be observed at the longer wavelengths only for the aromatic compounds. Okay, but the intensity of the R band it is going to be very less. So that's why even though B bands are also going to be observed at longer wavelengths for the aromatic compounds, you can easily differentiate based on the intensity, epsilon value. Okay, so molar absorptivity it is going to be very high for the B bands, comparatively R bands it is less. Okay, and the compounds which are giving this K type of the B type of the absorption bands are benzene, styrene and toluene. That means the chromophoric groups are going to be attached directly to the benzene ring. Okay, so this is about the absorption bands B band. Now let us move to the another band, E band. Alphabetically we are going. Okay, so B band we have completed. Now it is E band. So E band is also due to the pi to pi star transitions only. Okay, so in this way also you can easily remember. And if you have seen the B band is also pi to pi star, and next E band is also pi to pi star transitions only, and in which molecule we are going to see this type of the absorption bands means it is observed in 3-ethylenic double bonded compounds. 3-ethylenic, that means CH2 double bond CH2 ethylene group. Whenever you are finding any ethylene group in the particular molecule, you are going to see the formation of the E band in that molecule. Okay, that means ethylenic double bonds, whenever 3 groups are there, like simple example benzene. Okay, so in benzene also you are going to see 3 ethylenic double bonds, and mostly these are called as benzenoid systems, which are closed cyclic conjugation. Okay, so if you are going to see like this conjugation, whenever conjugation it is there, that means what is conjugation? Alternate double bonds are present, that is called as conjugation. Okay, so it is due to the C only, right? So whenever you are going to see CH2 double bond, CH2 ethylenic double bonds, 3 are there, then you are going to see the formation of the E type of the absorption bands. And here if you observe a simple for benzene molecule, you are going to see the 2 types of the E bands. E bands are actually 2 types, E1 and E2 bands. Generally E1 band, which is having very high intensity, you are going to observe, but it is going to be observed the short wavelength. That's why for some of the compounds you are going to see the spectrum is going to observe like this. At the starting itself, if you are talking about 180, 190, 200, 220, 210, 220, like this, if you are taking wavelength on this and absorbance on the y-axis, okay, then what happened? Some compounds you are going to observe the peak is directly coming from the highest scale value. Okay, that means these absorption bands here also you are going to see. Okay, so E1 band, it is going to be observed at the 184 nanometers, higher intensity value it is going to be there, but very short wavelengths. Okay, so that's why here it is 184, and E2 band is also going to be observed, that is at the 205 nanometers, which is having the lower intensity. Okay, that means here and around 205 means it is having the very lower intensity, lower epsilon value. Okay, but at the highest wavelength, comparatively 180 and 205, it is not the very highest range as compared to the UV range, but the difference it is going to be there. Okay, and the E bands are going to be observed in the compounds like benzenoid compounds like naphthalene and anthracene, more conjugated compounds. Okay, so in such cases you are going to observe this E type of the absorption bands. These are due to the pi to pi star transitions only, but here blindly you can remember that where you are going to observe the conjugation and 3 ethylenic double bonds are present, then definitely you are going to see this E absorption bands. Okay, now let us move to the another absorption band, which is very commonly occurring in most of the unsaturated compound, that is nothing but the K band. Okay, so K type of the absorption band, if you are going to see, that is also due to the pi to pi star. So till now we have seen B type of the absorption band, E type of the absorption band, and K type, B, E, K. These 3 are due to the pi to pi star transitions only. Okay, and these K bands are also going to be observed when the compounds are having conjugated double bonds. Okay, so conjugated double bonds, whether it is in diene compound or triene compound or polyene compounds or enones. Okay, acetophenone, like that. Okay, so you are going to see the compounds like dienes, polyenes, trienes, enones, such type of the compounds, you are going to see this K bond, K band. So it is also due to the pi to pi star transitions, and most of the common example for explaining this K band is 1,3-butadiene. So 1,3-butadiene, simply you are going to see the formation of the absorption band. Here you are going to observe the epsilon value, it is going to be in and around more than 10,000. Okay, so all types of the K bands which are going to have very high intense bands, and epsilon value it is going to be always more than 10,000. Okay, so thereby you can easily determine such compounds qualitatively as well as quantitatively by UV spectroscopy. Okay, and other examples like acrolein, styrene, that means the conjugated compounds, enes and enones. Okay, so all the polyenes, enes and enones, which are going to be having these K type of the absorption bands, but whenever these K bands are going to be observed, these are acting sometimes differently by solvent polarity. Okay. So, by increasing the solvent polarity, you are going to observe the intensity of this K type of the absorption bands. It is sometimes variation. It is going to be observed. Okay. Because whenever lambda versus epsilon, log of epsilon or whatever we are going to take. Okay. So, in this you are going to see the absorption bands like this, sharp peaks you are going to see, otherwise you are going to see the peaks like this, or otherwise something like this also you are going to observe. Okay. So, high intensity absorption means you are going to observe the K bands, but those E bands are also high intensity absorption peaks, but mostly you are going to see the B type of the bands here and K type of the bands afterwards. Okay. And high intensity bands E type here. R types means these are actually forbidden. Okay. So, alphabetically if you want to remember means actually that starts from B, E, K, R, but intensity wise if you want to remember means it starts from E. Okay. E, afterwards the high intense bond, that is K, then it is B. Okay. So, in this way you are going, the intensity wise these are going to be like this. Here in this case the intensity, it is less than 100 for R types of the absorption bands. Okay. And remaining you are going to see these are going to be K bands and E bands more than 10,000 you are going to see, and B bands means less than 10,000 you are going to generally observe. Okay. And conjugated compounds, definitely whenever alternative double bonds are present, you are going to observe this K band. K bands are generally more consistently you are going to observe, and most of the compounds with unsaturation you are going to observe this K bands. Okay. But E type already we have seen B bands and E bands are also, sometimes B bands are also going to be highly the consistency is going to more intense based on the compound. Chromophore, whenever it is attached to that benzene ring, then you are going to see high intensity B bands are also going to be there. Okay. Next, if you observe the last absorption band, which is nothing but the R band. Okay. So, R band, this is going to be caused by a transition, that is N to pi star. Okay. So, till now we have seen B, E and K, those are due to the transitions of pi to pi star, but here R band is due to the N to pi star transitions. Okay. So, that means whenever a compound is having any single chromophoric group, then you are going to observe this R band type of the absorption bands, mostly in the compounds which are containing carbonyl group, CO containing groups, and also in the compounds which are having at least a single lone pair of the electrons. Okay. Such compounds you are going to face this absorption bands, and generally these R bands are going to be forbidden transitions. Forbidden transitions means you are not at all observing these types of the R bands in the normal molecule. Okay. So, even though you are going to get it from the calculation point of view, from the graph, theoretically you can say that okay, this is going to be there and this is going to be calculated, but practically these are highly forbidden. Okay. You may not observe, only on the paper only you can say this is there. And compounds containing carbonyl group, that means like acetone, acetaldehyde, acrolein, in these compounds we are going to observe this R type of the absorption bands. Okay. So, what is the significance of this absorption bands means you are coming to know about the conjugation, the importance of the conjugation. Okay. So, wherever you are going to observe in some of the molecules, that means in some of the molecules if you see the conjugations are generally present in the aromatic compounds which are the benzene ring. Okay. But alternative double bonds like in dienes, octadiene, heptadiene, butadiene, okay, styrene, acrolein, all these are also going to be conjugation, it is going to be there. Okay. So, whenever you are going to see any type of the ethylenic double bonds are there, then based on the number of ethylenic double bonds, you are going to observe the absorption bands. That means, okay, I will tell you with explaining the graph itself. In this, if you are taking wavelength versus log of epsilon value, okay, then whenever based on the increasing the conjugation value, if you are going to see like benzene, naphthol, anthracene, that means the rings are going to be increased. So, the conjugation it is also going to be increased. Okay. So, for if n equal to 1, that means only one ethylenic bond it is there. So, let us say if the peak or spectrum whatever it is there, it is observed like this. Okay. So, in this case you may say that already from the other tests and all these things you have concluded that the one ethylenic bond has been confirmed. Okay. But with the increasing the ring, increasing the conjugation, you may see the shifting of the lambda max towards the longer wavelength also. Okay. So, thereby sometimes you are going to see the conjugation level also it is going to be increased like this. So, n equal to so in this case you are going to see either n equal to 2, that means number of ethylenic bonds are going to be increased. Generally not 2, actually 3 or 4 sometimes you are going to see. Okay. So, double bonds are going to be increased. So, whatever the peaks are there, the number it is going to give you the information that the conjugation has been increased. The ethylenic bonds whatever those are there, which are also going to be increased. Okay. So, in that way you will come to know whether in the reaction, kinetic reactions also, whether the complete conjugation has been done and the from the intermediate the final product has been formed or not in the synthetic reactions. Okay. So, all these reaction kinetics are also, it will give you some of the information. Okay. So, in this way these absorption bands are going to be helpful, because generally if you are seeing the UV spectroscopy at the molecular level, if you know about the electronic transitions sigma to sigma star and to pi star, so all these types of the transitions means that will give you an idea at which wavelength you are going to estimate the compounds quantitatively and qualitatively. But knowing the absorption bands, the significance of this absorption bands, that means it is going to give you the importance of the conjugation. Okay. So, thereby it will help you in the structural elucidation of the compounds, right. Hope this session is useful to you. Let us meet in the next any other session which is very interesting. Okay. Thank you students. Thank you for attending.